Hey everybody, what I'm going to do for you here is go through a complete AP Physics 1 question. This has been released publicly from the College Board, so it should be okay for me to do this. I'm going to, in addition to just solving the problem, I'm going to try to explain the physics behind it. Try to give a bit of a lesson within this question. So just an FYI, I'm not really going to focus on how much time that I'm spending because I'm not really trying to just answer this as a student. I'm trying to explain it as a teacher. Regarding the points, I'm going to be confident that my solution will give me most, if not all, of the points. I didn't really look closely at the published scoring guide, so it's entirely possible that I might not get full credit because once in a while they're looking for something rather specific. And just a disclaimer here that I probably will get all 12 points from the solution I'm about to write up, but it's possible that I'm not. Don't consider this to be in any way, shape, or form an official solution. This is just my take on it. Okay, so I'm going to get right to work here. The problem involves a fairly standard situation. There's a tabletop with two blocks connected by a string and a pulley. As a student, what I'd encourage you to do is read through the question from beginning to end kind of quickly, at least like the first section of the question. Just get a sense of what's going on and then start to pick out those details. So let's go through this. This problem explores how the relative masses of two blocks affect the acceleration of the blocks. Block A has a mass that's just designated ma, so that makes sense. Rests on a horizontal tabletop. There's negligible friction, so negligible means so little as to safely ignore completely. There is effectively no friction, so that won't be a part of this problem between the block and the tabletop. Block B has a mass mb, hangs from a light string. The word light is a bit of a kind of a code word in this kind of physics. The word light means that it has such a small mass that it too can be, for all intents and purposes, considered to be zero for solving the problem. So light string, effectively no mass, or at least a negligible amount of mass. That runs over a pulley, attaches to block A. So just verbally describing the picture that we're looking at, nothing new really being presented to us yet. The pulley has negligible mass. And spins with negligible friction about its axle. So it's a fully idealized pulley, which is very typical unless the question wants to explore that rotational dynamic aspect where we might have to factor in for like a moment of inertia, but that's certainly not the case here. It's an idealized pulley. The blocks are released from rest. Okay, so just intuitively, hopefully you can spot this. If block B is released, block A is released, the whole situation is allowed to move. The weight of block B is going to cause it to accelerate downwards. Meanwhile, because block A is connected by a string and there's certainly nothing opposing that horizontal motion, there's no friction, for example, block A is going to accelerate along to the right. And because they're connected by this string pulley arrangement, although they move in different directions with block B going down and block A going to the right, their motions are effectively synchronized in the sense that at any one moment in time, however fast block B is moving downwards, block A would have to be moving to the right with that exact same speed. And of course, that also means that any changes in speed or magnitude of change of velocity would have to be matched by that of A, other than the directionality, right? So that also tells me that the magnitude of the acceleration of the two blocks is also going to have to be the same. Okay, so let's get into the actual first question here. Part A, subpart 1 says, suppose that the mass of block A is much greater than the mass of block B. So just to explain much greater is effectively language that says not just a little bit greater, don't even think like 10 times greater, don't think 1,000 times greater. Much greater means like push it all the way. Like block A is vastly, like millions and billions and even beyond that times as great of a mass as block B. In other words, what they're effectively doing is they're saying, for all intents and purposes, the block B has negligible mass, at least when compared to block A. So block B has effectively negligible mass is kind of how I interpret that. A has a whopping big mass by comparison, so block B is not really contributing any meaningful amount of mass to this situation. The question then asks me to estimate the magnitude of the acceleration of the blocks after release. Okay, so the magnitude of the acceleration of the blocks, I'd already mentioned that they'll have to have the same acceleration. And in this part of the question where block A is so much more massive than block B, hopefully you can spot that if block B's mass is, for all intents and purposes, negligible compared to that of block A is not going to be noticeably able to accelerate. I mean, technically it should have some non-zero acceleration to the right, but if we're pushing it to that extreme where block A is so like wildly more massive, then that tiny, tiny, tiny pull from block B by comparison isn't going to really have any appreciable effect on block A. So they did say to estimate it. They're not asking for a calculation. Make sure that you're paying attention to the words that are used in these questions and answer the question. Honestly, it might sound silly, but that's the biggest, or at least the first concern that I have for students, is that they often don't pay enough attention to actually doing what the question specifies. They're asking for an estimate of the magnitude. In other words, they really want to see, I think ideally here, a value. So estimating the magnitude of the acceleration of the block, and again, in this situation with block A being wildly more massive, any acceleration is going to be very, 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 very small. How small would depend on the exact values here, but if you push it to that extreme, I think I'm willing to say that block A will have a, quote, negligible acceleration. So in answering the question, I'm just going to say that the acceleration is going to be very nearly zero. And that's really all you have to say. In this part of the question, it's not asking for us to explain, although that's coming up right away. Oh, and actually, hang on, I just realized that I wrote that in the wrong space, but fortunately, since this is a tablet, I can just really quickly move that over. So in subpart 1, that's all they asked me to do. Estimate the magnitude of the acceleration. Please, when you're writing AP exams, or really any test or exam in the future, try your best to answer the question, and that's it. Move on. Don't try to throw extra information in here. Don't do anything beyond what you've been asked to do. Of course, this question is going to continue into asking us to explain our reasoning, etc. But that's it. Move on. I've answered the question. You want me to estimate it? I've estimated it. It's going to be practically zero. Now, of course, the continuation of the question is explain your reasoning without deriving or using the equations. So the AP exam especially does tend to give extra importance, like beyond what would be often the case in an introductory course or a typical high school course. It really gives or places heavy emphasis on a conceptual understanding of what's happening. So in asking us to avoid using equations here, they're really wanting us to prove to them that we understand what's going on. And I've already verbally described that to you. I mean, with A having such a ginormous mass by comparison, I've already explained it to you. So let's see if I can try to write that in a clear, concise way. And again, that's something that you should be striving to do when you're writing your exam questions. Be brief but complete. Be clear and correct. Don't provide anything that has not been asked. Answer the question and move on. Okay, so if I were to write this up in words, trying to be relatively brief here, I would say with because mass of A, in fact, let's just say it this way. I'll go back to my pen here. With the mass of A being much greater than the mass of B, the mass of B is effectively, and of course you don't have to use this wording, as long as you're communicating the idea across, you'll be fine. The mass of B is effectively negligible. Okay, so with that said, I have to make sure that I explain what my actual answer was. I don't think I've done that yet. I think this is an important kind of starting point, but why is it not going to accelerate? Or why is the acceleration going to be so nearly zero? Okay, so the mass of B is effectively negligible. This means that the force of tension, and you can use symbols in your explanations. I'm not using equations or deriving anything here, but feel free to kind of put things symbolic, especially, you know, measurable or quantifiable things like the mass of A or the tension force. This means that the tension force will be much smaller than the mass of A, and so with a small net force and very large mass, although, you know what, I might use a slightly different word at this point. Saying large mass would not be wrong, but I'm going to just kind of convince whoever's reading this that I really know what I'm talking about. I'm going to say inertia. Inertia is that property of mass that makes it difficult to accelerate. So it has a very small net force, it has a very large inertia. Its acceleration, let me come right back to my answer here to kind of justify it. Its acceleration will be very small. In fact, I'll just say well approximated to be 0. Okay. So that's probably good enough for me. I think anybody reading this, and of course that's the mindset you should understand that the people who are ultimately going to be grading these questions have. They want to make sure that you understand your physics. They're going to be following a very clear kind of scoring guideline that is going to be looking for these key details. Okay, and I think that I would have satisfied those details at this point. So I'm going to continue on with the next part of the question. Okay, so the setup is fundamentally changing now. In part A, subpart 2, it's saying, now suppose that the mass of block A is much less than the mass of block B. Okay, so in other words, block A's mass is so small that, for all intents and purposes, it's essentially negligible. It's effectively nearly massless, so little mass. So block B has a substantial amount of mass, but block A has effectively negligible mass. So if I just temporarily go back to the picture, let's just kind of think that through. If I am now, and I'll just temporarily kind of use a highlighter here. So if I'm now thinking that block B has a lot of mass by comparison, and block A has a very, 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 very small amount of mass, it's the exact opposite of the situation we just looked at. With block A's low mass, it is super, super, super easy to accelerate. In fact, it offers practically no resistance to accelerate with that low mass, low inertia. So that means that block B is practically able to fall down nearly, and I think well approximated to be not at all, hindered by the presence of block A. Block B, I mean, just think of it. If block B was like just to get the point across, 1,000,000 kilograms, and I tie it to a speck of dust. Imagine that's what it is here. It's a little speck of dust, and of course it's a perfect string pulley arrangement. That speck of dust is not really going to hinder the fall of my giant boulder, which is kind of one way to visualize what this part of the question that we're dealing with is describing. So let me continue and actually answer their questions. Okay, so it says, again, estimate the magnitude of acceleration of the blocks after release. Well, I'm thinking that they're going to fall with very, very nearly the acceleration of free fall. So I'm going to say that the acceleration, in fact, I'm just going to say it this way, will be well estimated to be free fall acceleration, which I often use a number of 9.8 meters per second squared. On the AP exam, they're certainly happy to round that off to 10 meters per second squared, so that would have also been acceptable, certainly. But I think I'm just going to leave it as that. That's the number I tend to go with most often. And again, notice that I've answered their question, at least for this part, and I'm moving on. Okay, I'm not going to stay here any longer than I have to. And certainly if I was a student writing this, I would have moved on long ago. I'm just talking to you guys to help you understand what's happening. So the continuation of this question says, explain your reasoning. And again, I've already kind of described it verbally, so let's see if I can come up with a concise way of describing that in words. Okay, so again, so A is the one that was on the tabletop, B is the one that's falling. Okay, so now the mass of block A is negligible compared to the mass of B. So block B is able to fall with essentially no impact from the presence of block B. And again, coming right back to my answer, because that's what I'm trying to justify. I'm trying to explain how I arrived at that answer of 9.8. So the blocks will therefore have an acceleration of very nearly free fall. And maybe just to wrap that up, 9.8 meters per second squared. Okay, I'm probably being wordier than you need to be, but again, I'm trying to be very, very clear here. Nonetheless, that should get the physics across. Block B is able to fall practically without hindrance from block A. Okay, now moving on. Part B is switching things up from what we've just been doing. It says, now suppose that neither block's mass is much greater than the other. So their masses are more similar to each other. I think that the gist of this is I can't ignore either of their masses. Whereas in part A, they took turns effectively having negligible mass. But they're not necessarily equal. Okay. The dots below represent the blocks A and B as indicated by the labels, sure, okay, and don't let the fact that they're now circle in shape throw us. We often just use small circles or almost even dots to represent physical objects, so the switch of a shape is not relevant, but I'll just point it out. On each dot, draw and label the forces. Don't resolve anything into components exerted onto that block after release. Represent each force by a distinct arrow starting on and pointing away from the dot. So this is pretty standard wording for essentially asking us to draw free body diagrams. So they want a free body diagram for block A using the dot as the object. Block B similarly is that other object. They want effectively two separate free body diagrams. So if I just scroll back to remind us of what's going on here, block A is on the tabletop. So vertically, it has a force of gravity pulling it down, and of course the tabletop is supporting it with a normal force, right? That perpendicular to the surface support. So up, normal force. Horizontally, the string is pulling it to the right. We can call that a tension force. And of course, reminder that there's no friction, negligible friction. So horizontally, I'm going to leave it as just that one single force pulling it to the right. Okay, so let me actually go to my diagram and draw that in. So I'll draw a downward force vector, and I will label it the force of gravity. Of course, they're pretty accommodating with the labels that you use, so if you're in a class or using a book that uses slightly different notation, as long as it's anywhere near remotely a common notation, you'd be fine. So I'm using force of gravity, Fg, as my standard notation, but it doesn't have to be that exact same label. Similarly, the upward force would be a normal force. My label for that is Fn for normal force. Both of these are quite common labels, so there'd be no problem with that whatsoever. Horizontally, there's also that tension force, so I'll sketch that in and label that Ft. And I think that's it for block A. Those three forces are present on block A. Meanwhile, block B, if I just remind you of that situation, block B has been released, of course, so there's no applied force on either of these, just to remind us of that. So it'll have a force of gravity pulling it down, of course, and of course that tension will offer some, the string will offer some tension, pulling it upwards with that tension force. So I'll go back to my diagram, and okay, so I will draw a downward, actually here, let me just kind of get that a little bit, there we go, force of gravity and an upward force of tension. Okay, I think that's good enough for me. On a free body diagram like this, unless it's specified otherwise, we don't really have to worry about how long that we're drawing these vectors. It's kind of nice if you can draw them a bit to a scale, but typically, unless they specified it, they're not really looking for a scale. In other words, I can actually tell you for sure that the force of gravity on block B would be larger than the force of tension. Like physically, it would be, because it would be accelerating downwards. I've drawn the arrows of a very similar length here, and I'm not worried about it. Like, I'm not trying to convey visually that the force of gravity is larger than the force of tension. In fact, I tend to draw all of the arrows of at least a similar length, unless there's a reason to do otherwise. So I think that would be fully adequate for part B. Part C. Derive an equation for the acceleration of the blocks after release in terms of MA, MB, and physical constants as appropriate. If you need to draw anything other than what we've already drawn, do not add anything to the figure in part B. The reason that they're saying that is because when they ask for a free body diagram like this, even though they didn't use that phrasing, what they definitely do not want to see is anything in these force drawings other than forces. So I will temporarily, because this is a big no-no, let me just put it into to clearly communicate what I mean by that. If I had said, oh, by the way, I know that block A is accelerating to the right, and let's just say that I kind of slip that in a vector representing the acceleration, and oh, I know that this one's accelerating downwards. So those acceleration vectors, I mean, in principle, are not incorrect. It's true that block A would be accelerating to the right and block B would be accelerating in the downward direction. So those are true statements, but that would definitely get us in trouble on this exam. If we were to draw non-force vectors in something that we've been clearly asked to draw only the forces. So big no-no. I'm going to get rid of them. I just drew them in so I could have that conversation, but I'm definitely not wanting them to be there. Okay, so they want me to now derive an expression for the acceleration of these two blocks. Now, there's more than one way to do this. One really nice way would be to treat them as a single system, and that single system has a combined mass of MA plus MB, and effectively the net force is the weight of block B. I would consider that to be a bit of a shortcut. You're kind of resolving effectively around the pulley, but just in case you haven't seen a method like that, I'll avoid using it here. And instead what I'll do is a slightly longer solution that will look at each block as a separate object. I'll basically write equations for each object's acceleration, and then I'll kind of bring it all together to get what they've asked me to find. Okay, so here's how I'll do it. In fact, let's start with block A. Okay, so block A. Okay, here we go. Block A. Okay, now I know that block A is going to accelerate to the right. I know that vertically there's just a balance of forces. So I think that I can say that thinking of horizontal, okay, in fact, maybe I'll even just sketch in a quick little, actually, you know what I'll do is I'll define a y-axis to point downwards. That'll be useful in block B right away, and an x to the right. So this little picture that I've just drawn in effectively communicates to anybody looking at my solution that in what I'm about to do, I'm going to take the x coordinate to be positive to the right, and I'm also going to take the y to be positive in the downward direction. That'll be more useful for block B right away. Okay, so here we go. Block A, if I look at just what's going on in the x, it is certainly accelerating, and that will be in accord with Newton's second law, equal to the net force divided by the mass. So if I'm specifically thinking of block A, the acceleration of A will be equal to the net force on A divided by the mass of A. The net force is the tension force. It's the only force that's pulling block A to the right, and I can see that from my force diagram. So horizontally, it's the one and only force. So I'm just going to say that the acceleration of block A is therefore equal to the force of tension divided by the mass of A. Great. Meanwhile, block B is going to be accelerating. I know that it's accelerating downwards because that force of gravity certainly will be larger than the tension force. So I can write a similar statement about it, although I'm focusing on the vertical here, so I'll just kind of designate a y to communicate what I'm thinking. I'm just looking at that y coordinate, or sorry, the y component. The x, there's actually nothing going on for block B at all. So in the vertical, block B is also accelerating. The acceleration of B, and as always, that should be equal to the net force on that block divided by the mass of that block. I find that that's a mistake a lot of students make with Newton's second law, is they kind of write the equation correctly often, A equals net force over M, or net force equals MA, but then they start mixing and matching incorrectly, like the acceleration of that object over there is equal to the net force on something somewhere divided by the mass of something else. No, Newton's second law doesn't work that way. You need to consistently apply it to one single object or system. In this case, just block B over here and separately block A over here. So the acceleration of block B is equal to, since I'm thinking of downwards as my positive direction here, I can actually say that there is a force of gravity on this block, and there is a negatively directed force of tension. That negative is really because it's upwards, and I'm treating down as my positive direction as communicated over here. So if I divide that by the mass of block B, that should be pretty good. I'll just substitute the force of gravity to be m of B times g. So the acceleration of B is equal to m of bg minus ft, just to write it in a simpler way, divided by the mass of block B. All right, now don't lose track of what we're after here. We are trying to find an equation for the acceleration of the blocks after release. Okay, now you might say, well, that is the answer to this question. It's an equation for the acceleration. And actually, it is. In fact, you could say the same thing about this over here. That also is an acceleration or an equation for the acceleration. So that, I mean, that's factually true, but neither of these would be considered to be correct for the question that we are being asked to find, because the question actually says, just to kind of continue this, in terms of MAMB and physical constants. In other words, we're not allowed to have any other variables inside of our answer here. And at the moment, I have the force of tension in both of these. So because of the force of tension being present in these two equations, neither one of these equations is what they have asked me to do. It fails to meet the objective. So let me just kind of get rid of all that highlighting just to kind of focus on what we're doing here. And let me continue because I'm not yet done. So I am trying to find it in terms of MAMB and physical constants. In other words, lowercase g is fine. I mean, that's considered to be a physical constant in this context, at least. Arguably, you could say it's somewhat of a variable, but it's so commonly accepted as a physical constant that we're just going to go with that. Okay, so the way that I'm going to pull that off is by realizing that because both of these have force of tension in it, I can actually combine these equations to basically effectively remove that force of tension from what I will then consider to be my final answer. How about if I do it this way? And I'm going to switch colors just for your benefit. I wouldn't normally do that if I was just writing up a solution here on an exam. So if I solve this equation for the force of tension, thinking of, originally block A's equation, the force of tension is equal to mass of A multiplied by the acceleration of A. This means that anywhere that I see the force of tension, like for example over here, I could replace it with what force of tension is equal to, m of A times the acceleration of A. So let me go ahead and do that over here. So the acceleration of B is equal to the mass of B, let me just make that a bit clearer, the mass of B, G, minus the force of tension, which I'm going to right now do that substitution here, the mass of A, acceleration of A, all of which is over the mass, oh, actually I should be doing that in blue because that's not part of my equation that I pulled in. So all of which is over the mass of B. Okay, now I'm almost done. I don't want to spill into the next page here, so let me just, you know what, let me give myself a little bit extra room here. I'm just going to take that, pull it to the side like there. And let me just continue in here. I'll use another color just so it stands out here. This equation is almost what I want. I want an equation for the acceleration in terms of those physical constants. And here's where I'm going to remind you of what I said a little while ago. In fact, I think it's one of the first things I said. The acceleration of A and B are the same. Okay, the magnitude of the acceleration is exactly the same. And I've designed these equations so that they're even both positive within their each separate equations. The acceleration of A is certainly positive because it's going to be accelerating to the right in the x. Meanwhile, the acceleration of B is also positive because it's accelerating in that downward direction, which I've designated as positive. So the truth is, I can take advantage of the fact that the acceleration of A and the acceleration of B numerically are identical. So how about if I just record them both as A, which is what they've been asking me to find, right? Just the acceleration of the blocks. Well, they both have the same acceleration. So let me actually take this equation in here, and I'm going to drop the subscripts on the accelerations. So the acceleration of the blocks is equal to m of b g minus mass of A acceleration of the blocks. And let me also, well, here, I'll just do this to save myself a step here. Rather than show the division of mass B, I'll just multiply the mass of B over for a moment. Okay, now, all I have to do is solve this equation for acceleration A. To do that, I will maybe add this term to the left side of the equation. So let's add m of A times A over mass of A times A, plus the term that was already sitting here, mass of B times A, mass of B times A, and that will be equal to the mass of B times G. Let me just tidy that up a little bit. The mass of B times G. I can then factor out the A from that side of the equation, the acceleration times mass of A plus the mass of B, equal to mass of B G, which means that I can have the acceleration equal to the right side of that equation, mass of B G, divided by taking this summed combination of the two masses, dividing it to the right side of the equation, mass of A plus the mass of B. Okay, now let's just verify that I've answered the question. What did they want me to find? They wanted me to derive. Okay, now derive, I probably should have mentioned this a moment ago. Derive itself means that they want me to show the process of how this equation is going to come to be from what we generally consider to be first principles or generally acknowledged formulas, things like Newton's second law, for example. So starting from first principles, I have to show them how I'm going to arrive ultimately at this equation. I think I've done that. I've shown in my solution something that anybody who has a good understanding of physics, and that's the mindset you should have. You're trying to write up a solution so that somebody who already understands physics would be able to look at what you've written and say, oh yeah, that makes sense, oh, I got it, the math all follows, it's all good, oh, I see what they're doing over here for block A, that all follows, that makes sense, I understand, got it, and ultimately arriving at your end answer, or in this case, equation. So that should be your objective. You need to communicate what you're doing so that somebody who is good at physics can make sense of what you're doing without having to do it themselves. If they look at your write-up and they say, okay, I have no idea what this person is even trying to do here. I mean, I could do this answer myself on my own page, but if I'm just trying to look at what they have done, I don't get it. I mean, they're losing me. They're not showing me something. This showed up out of nowhere. I don't know what that even means. You have failed to derive it clearly. Okay, so have I answered the question? Derive an equation for the acceleration. So this starts off with A equal to, so that's exactly what they'd asked me to find. In terms of MA, MB, and physical constant. So let's just verify. I have MA and MB. MB appears twice, which is totally fine. And G can be considered to be a physical constant. So I would say that is a satisfactory conclusion to this question. I think that I've done exactly what they've asked me to do. So with that in mind, I am going to move on. But before I do, maybe I should just mention one thing real quick. This might seem like a really sticky point here, but it's important. Anytime on an exam question like this that they present to you kind of like a symbolic, like lettering for something, like this is M subscript capital A, and also M subscript capital B. So it might sound like a sticky point here, but do not change that notation. I had mentioned earlier that they're pretty flexible on things like, I don't know, like the symbol used for the force of gravity. If you had used a slightly different, just notation for that, if you had called it, for example, well, even something like, even though I wouldn't advocate for this, some people will use like a capital W for weight. I really don't think it's a great notation because I think it gets confused with other things like work. But it is fairly common. So if somebody had used a W here, they would have accepted it. Okay, W for weight. Again, strongly not my preference, but it would have been okay. Over here, if I had said, M of A, imagine that I had done this, and I'm not wanting to do this. Imagine if I had just said, I'm just going to call this like A, and I'm just going to call this B. I'm going to lose the M completely. Imagine that I then write it up so that appearing here is just nothing but a B, this is just an A, and this is a B again. Strictly speaking, that would not be correct. Do not substitute. They're asking me to do it in terms of exactly this notation, so stick with exactly that notation. That's not very flexible at all if they have defined quantities such as that. I'm going to move on here to part D. Part D says, consider the scenario from one of the earlier parts. So part A, subpart 2, I have to remind myself of what that was again. Okay, so subpart 2, yeah, right here. So A is the one that is very much less than the mass of B. And I was supposed to back then estimate the accelerations, and I said it'd be basically that of free fall, right, 9.8, and I explained it. So A is much less than B. Okay, A is much less than B. So they're basically saying, hey, back then, when that was the case, in fact, maybe I could even remind myself, mass of A is much less than the mass of B. I don't think there's any problem with just kind of a little notation out there to remind myself of what's happening. That would be okay. So considering that specific situation, oh, in fact, they actually reminded me of it. The mass of A is much less than the mass of B. I should have kept reading. I didn't have to scroll back to remember that. The question is, does your equation for the acceleration of the blocks from part C, so what I just came up with a moment ago, right here, this expression for A, or this equation for A, does it agree with my reasoning way back then in that earlier part of the question? Yes or no? Now, again, answer the question and move on. Well, if you're writing this up for the very first time, you might not at this moment in time know the answer to that. Yes or no? I mean, I don't know. But of course, there's a follow-up question that says, briefly explain your reasoning by addressing why that it does, why, according to your equation, the acceleration becomes or approaches a certain value when the mass of A is much less than the mass of B. So how about if I actually kind of, nobody's going to know, upon reading my completed solution, I mean, you're going to know because you're seeing me do it. How about if I actually try to kind of do this here just to verify whether my equation does or does not agree? Okay, so how about if I start with exactly my equation again here? So, in fact, since I'm using a tablet, I'm going to be a bit lazy. I'm just going to take that and copy it so that I can come down here and paste it in. Okay, so this was my equation that I had derived. Okay, now, how can I explain why, according to the equation, the acceleration becomes or approaches a certain value? So just to be clear here, when they ask me to explain, they're asking for not just math. I think that we can refer to equations and we can even maybe do some math within our explanation, but the word explain means you need to convince us that you know what you're talking about. So don't just slap down some equations and symbols and math. You can use those as part of your tools to explain, but when you see explain, try to understand that their intent is convince us through your written response that you understand this. Okay, that's what I would interpret explain as. I mean, that's kind of like the underlying reason that they're asking me to explain. Okay, so how can I convince them that that given that situation where the mass of A is much less than the mass of B, that something interesting is going to come from this? Okay, so let me get to work here. And again, remember that I'm going to use words here to explain what I'm doing. Okay, so how about if I say, if the mass of A is much greater than the mass of B, then the mass of A plus the mass of B is very nearly, let's say, is very nearly. Now let's think about it. What is 1 trillion, okay, just to give you some impression of what I'm thinking here, what is 1 trillion plus 0.000000, a whole lot of zeros, 1 at the end of that? If you are adding two numbers, one of which is much larger, now remember, we're not saying a little bit larger, we're saying like much, much greater, then that teeny tiny little bit extra is generally negligible, right? It's safe to treat as if it were essentially zero. It's very nearly equal to, let me just continue, very nearly equal to MA. So with that in mind here, so the equation can be written as A equal to, and remember what I'm saying is they add together to be something that is essentially equal to the mass of B. So the mass of B, G, over the mass of B, basically. At which point, and let me just remind myself coming up here, yeah. At which point, the acceleration is equal to G. Okay, now, because they did want me to explain this, I'm not going to leave it as that. I just want to make sure that, again, whoever's reading this, I understand this. So explain briefly your reasoning. According to the equation, the acceleration becomes or approaches a certain value of A. So, in fact, let me just read it. Maybe I've done a good enough job. If the mass of A is much greater than the mass of B, then they add together to get very nearly the same thing. So the equation can be written as that. And so A equal to G. Actually, you know what? I think I'm going to leave it as that. I think that I've already explained it well enough. I could continue on here and kind of just fluff that up a little bit, but generally, that's not in your best interest. If you have done a good job of answering the question, it is usually not to your advantage to try to like add on extra information or try to shovel on, irrelevant information is even worse. If I were to continue on and try to bedazzle somebody with my profound knowledge of physics and make a mistake, that will certainly hinder my outcome. Meanwhile, if this is already correct, I'm done. I think I should have full credit on this already. So anything that I add to this will certainly not help me, and it potentially could hurt me. So I'm going to move on. Okay, so there we go. Moving on to part E of the question. The question is now, while the blocks are accelerating, the tension in the vertical portion in the string is T1. Okay, so while the blocks are accelerating, T1. Okay, so T1 is that vertical, and let's make sure that we don't screw this up. The vertical portion of the string is what they're calling out. So let's not get distracted by looking at the horizontal portion. Okay, next, what happens is there's fundamentally a change. They're changing the setup from what we've had previously. The pulley of negligible mass, which is the pulley we've been assuming we've had all this time for all preceding parts, is replaced with a second pulley whose mass is not negligible. So we've been dealing with an essentially idealized pulley. E is saying, what if it's not? What if it's not idealized, at least in the sense of the mass is no longer safe to ignore? When the blocks are accelerating in the scenario, the tension in the vertical portion is T2. Okay, so let's think of T1 as, in the case where the pulley is idealized, and T2 is the new case, the case in which the pulley has a mass that can't be ignored. How do the tensions compare to each other? And they're basically giving us what is essentially a multiple choice question within. We're going to have to choose which of these three cases. Is it, the same? Is the second new tension greater, or is the second new tension less? Well, in this question here, you might not feel confident yet choosing which of these three that it is. So how about if I go back to the diagram and think this through, and maybe I'll even come back and start kind of reasoning my way through this, within my reasoning, I hope to discover the answer. I'll then go back and kind of circle which of the three that I come to the conclusion that it must be. Nobody will know that I've answered it in that reverse sequence if they're only looking at my final written work here, right? So you'll know because you're seeing me solve it, but nobody else will know. It's not like you have to psychically know the answer before you think about it. So let's try it that way. We're going to go back to the diagram and reason this through. So we're focused on the vertical string only. And the question is, up until now, the pulley has been magically massless. Negligible mass, and boom, all of a sudden the pulley has mass that can't be ignored. Okay, well, what I'm thinking of now is basically a rotational piece that I have so far been ignoring. With this pulley having a non-ignorable mass, it has a non-ignorable moment of inertia. And of course, as block B falls down, accelerating faster, 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 necessarily, if this string, which I think is safe to assume is not going to just slip across the surface here, it's going to have to accelerate this pulley to spin faster and faster and faster. Now, with no mass, which was the original case, that's fine. I mean, it essentially does that with a negligible net torque, negligible moment of inertia. In other words, you could safely ignore that aspect of the problem. Not anymore. So the new tension here, so the tension shifts from the original T1 to a new T2. Hopefully you can, I mean, intuitively, if nothing else, spot this. The addition of mass here is going to make it harder for the block B to accelerate downwards. Previously, the fall of block B, in effect, was driving block A to accelerate. Now, it's also driving a pulley to spin with increasing angular velocity. So, if anything, block B is going to have a reduced acceleration. Why is it going to have a reduced acceleration compared to before, when the pulley was negligible mass? Because, and this is, I think, the answer to the question that we're getting at, I'm just going to temporarily think of it in here. There was a force of tension, there's a force of gravity. Now, when it was spinning freely, when the pulley was idealized, we had a good, so let's just think of it as a good size acceleration. It was accelerating really well. All of a sudden, we, in fact, let's just think of it this way. T1 was the notation that they're using here. Okay, so all of a sudden the addition of mass here kind of sort of hits the brakes in a way. Block B will continue to accelerate downwards, but less well. With a reduced acceleration, it must be the case that there is a reduced net force. How can there be a lesser net force? Well, if the force of tension itself got bigger. The force of gravity will still be the larger of the two. I mean, it's still going to be accelerating downwards. But with the force of tension, think of it this way, as getting maybe closer in size to the force of gravity, there'll be less acceleration because of it. Okay, so I think I've convinced myself of the answer here. The new tension is going to be larger. So the new tension will be larger because of the addition of mass here. Let's see if I can go write that up. Okay, in fact, I'll do what I suggested I would do. I'll kind of explain my reasoning, and then once I've convinced myself of it, I'll kind of commit to which of these three it would be. So explain your reasoning. Okay, so let's say adding mass to the pulley. Pulley means that we can no longer, because without stating it, I have been, we can no longer ignore its moment of inertia. Its moment of inertia. By the way, moment of inertia is quite often also referred to as rotational inertia. Inertia. Okay, so let's just slip that in. I think either term would have been acceptable here, but I'll just show you both in case you've come across one and not the other. Okay, so we can no longer ignore its moment of inertia because it will be harder to spin the pulley now. The system will have a reduced acceleration. Okay, so it'll have a reduced acceleration. Let me add a little diagram here. So this was the mass of block B, the hanging mass. It had a force of tension, and it had a force of gravity. And you know what? How about if I remind myself here that they were just using a T here, so maybe I'll be consistent with that. I'll just call that T. Okay, so block B will still accelerate down, but less than before. Okay, so the new tension T2 must therefore be closer to the weight of block B. Okay, so closer to block B, which can only result, let's just say it this way, which means the tension must have increased, leading to a smaller net force on block B and so a smaller acceleration. Okay, so, and let me not forget here that since I think I've convinced myself and I think that this physics is sound, I'm going to go back here and just circle the one that is consistent with what I just said. The new tension will be larger than it used to be, so that's the first choice right here. So the new tension T2 is greater than the original tension T1. By the way, make sure you don't miss that. I've been kind of reminding you throughout this whole solution that you really make sure that you've answered the question. So without circling that, I really would not have answered this question, and that would jeopardize whether this even makes sense. Like, briefly explain your reasoning. Well, how can I explain my reasoning if I haven't come to any stated conclusion? Okay, so without this indicated as being my choice, there'd be, I mean, really nothing to explain. So don't miss those little things here. Okay, I think that's the end of the problem. So yeah, that took me, that took me over an hour or just nearly an hour to explain. So a friendly reminder here that if you just sat down and solved this problem, you should be able to complete it within the allotted estimated time here of 25 minutes. The only reason it took me considerably longer than that is because I was trying to take advantage of this problem to communicate to you, whoever's viewing this video, what's going on, try to explain to you the physics. It certainly took me much, much longer to explain it than it would take you to just solve it.